Good day, everyone. This is linear algebra 2 from test 204, and we're having the 2 unit course. In this course, we are going to look at 6 outline. The first one is a review of matrices. The second one is a system of linear algebra, linear transformation, Cayley, aligning, then the diagonalizations of symmetric matrix, while the last one we look at bilinears and quadratic form. For this, we are going to look at the study section 1, which is a review of matrices. When we are talking of a matrices, what does it mean? It's an array of numbers arranged in row and column. The matrix is of order m by n, which is written as m multiplied by n, where your n is the numbers of row and your n is the numbers of column, and it is being represented as follows. Each number, as you have your matrix A now, which is a matrix of order m by n, each number aij is the matrix. In the matrix, is refers to as the elements. You have the elements, the numbers are in the chord brackets. The figures you have in that chord bracket is what we call the elements. I and j represent the I row and the j column respectively, in which the elements appear. A matrix is called real or complex according as it is elements. That is, if the numbers are real, so we call it a real matrix. And if the figures, what you have there, the entries, if they are complex, you call them a complex matrix. Then we have what we call a triangular matrix. When do you have a triangular matrix? When your n is not equals to n, that is, the numbers of row is not equals to the numbers of column. In such a matrix, we call them a rectangular matrix. And in the other way around, if you have your n to be equals to n, that is, they have the numbers of the order of the entries, the column now, your n and your n, if they are equal, then you have it as a square matrix. If a matrix has only one row, irrespective of the numbers of column, we call them the row vectors. That is, you have your RV, we have the element, the entries there. Like the example we have here, we have A11, A12, to A1n. That is a row vector. You are having just a single row with several numbers of column. Then we have what we call the column vectors, where you have just a single column, or you can have as many rows as possible, but just a single column. That one is called the column vector. And this column vector can be transposed. That is, when you are talking of a transpose of a matrix, we are talking of rearrangement of that matrix. If it is a row before, you change this to a column. If it's a column, if you want to find the transpose, it will change to row. So that it denotes the transpose. Column vector, your CR, which is a A11, A12, A1n. You put in a bracket, then transpose. That is raised to power t. That your t is what we know as the transpose of that matrix. If your n is not equals to n and is not equals to 1, as I've explained, in that case we have what we call the rectangular matrix. And if they are equal, if your m is equals to n, you have a square matrix. It can either be real or a complex, depending on the value you have as an entry. So when you have a complex number, you know what it means to have a complex. When you are having the root or high, so you are having a complex. So the elements you have there will determine whether it's complex or a real one. Then let A and B be two matrices of the same order. The two matrices are equal if and only if your Aij is equals to Aj high, where your Aij and Aj high are the elements of A and B respectively. That is, if they are equal. If they are equal, your Aij will be equals to Aj high. Then the next one, we look at the operations. And when you have a number, you can perform the basic operations on them. When you have your addition, you have your subtractions. So the same thing is applicable to our matrices. We want to look at the addition and subtractions of matrices. Two or more matrices are addable or subtractable if and only if they are of the same order. Before you can add or subtract any matrix, they must have the same order for that addition or subtraction to be able to work out. Their order must be the same. If your A is of order 2, that means your B, your matrix B must be of order 2. If A and B are two matrices of the same order, then A plus B is equals to C. That is the matrix A plus or minus matrix B. You can either add or subtract. So you get another matrix, which is your C. Now when you are adding, you are not just having a single value. You are going to have your results as a matrix. Your result will be in a matrix form. So that is why we have C, matrix C. That is your Aij plus or minus Bij is equals to Cij. That is, when you are adding two matrices, you are adding matrix A to B. Your row, the first row on your matrix A, you add it with the first column on your matrix B, then it will give you the first element in your C, in your matrix C. That is, you have Cij. That is the addition of the first row and the first column. So you continue in that order till when you have your matrix C. Note, matrix addition is commutative. What does that mean? It means that you can decide to add A plus B, or you take it as B plus A. When you do that, you have the same answer. That is what it means to be commutative. It doesn't mean, the arrangement now doesn't matter. You can decide to add A plus B or B plus A. You will still have the same result. That is commutative. Then we have the associativity. A matrix addition is associative. That is, A plus B into bracket plus C is equals to A plus B plus C in bracket. That is, you can decide to take your matrix A, add it to matrix B, your results, add it to matrix C. Or you can decide to take matrix B and C, perform the addition, add the two together, then take your matrix A and add it to that result of B and C. You will still have the same results. That is what you mean to say a matrix addition is associative. Then the next one, we look at the multiplication of matrix by a scalar. What do you mean by a scalar? It's just a number, a constant used to multiply a matrix. So if A is equals to Aij and lambda is any scalar, that is any number, you can take any number, any constants, then lambda A is equals to A lambda. That is, you can decide to put the constant at the back or put it at the front. You will still have the same results. Then we look at multiplications of matrices. If you are given two matrices now, you want to multiply matrix A by B. How do you go about it? A multiplication algebra is defined on a matrices A and B if and only the numbers of matrix A is the same as the numbers of row of matrix B. That is, that multiplication can only be possible if and only if the numbers of column, the column you have in A is the same as the numbers of row that you have in B. Let's look at a practical example now. We have our matrix A to be a matrix of 1, 2, 3, then 2, 1, 4. While your matrix B is 1, 2, then 2, 1, minus 1, minus 4. What does that mean? That your A now, we have 2 rows and 3 columns. That is a matrix of 2 by 3. 2 rows and 3 columns. Then you have your B, which is 2 by 3. That is, you have, okay, 3 by 2. You have 3 rows but 2 columns. 3 rows, 2 columns. And your A is 2 rows, 3 columns. This can only be possible if you have it this way. The multiplication can only be possible if you have it this way. That is, the numbers of row of B must be the same as the numbers of column in A before that multiplication can be possible. So let's look at the product now. A multiplied by B. The first row, which is what are the elements you have in the first row? You have 4, minus 2, minus 3. Use it to multiply the first column on a matrix B, and you have it as 4. When you perform the simple operation there, the arithmetic operation there, the result will give you 4. Then take the first row on A to multiply the second column on B. When you do that, you will have the result as minus 8. That is 4 multiplied by 2 plus minus 2 multiplied by 1 plus minus 3 multiplied by minus 4. So when you find the addition and subtraction, you will have it as minus 8. So you have done the first row now for the products. We are left with the second row. So take the second row of element of a matrix A. That is the elements you have in a matrix A, the second row. Use it to multiply the first column in B and the second column in B. You will have your result as 1 and minus 11. So the product now, the product of the two matrices has given us a matrix C, which is a 4 minus 8, then 1 minus 11. Note this, in general, a matrix multiplication is not always commutative. It's not always commutative. What does that mean? You can still recall that when you are doing when you are performing an operations on the matrix A and B, when you are adding, you can add A plus B to be the same thing as B plus A. But in this case, not commutative. We are saying that if you are multiplying A by 2, A by B, that is matrix A multiplied by matrix B, is not always equals to multiply B, matrix B by matrix A. It's not always commutative. So there are some cases you may have it, but it's not a constant thing. So you should note that multiplication, matrix multiplication is not always commutative. Then another thing to note, F dot A is defined if and only if A is a square matrix. That is, if you want to multiply matrix A by matrix A, that means the matrix A must be of the same order. There must be a square matrix. That is, the numbers of the column must be equal to the numbers of row for you to be able to multiply them. Then the last one to note, if A is a square matrix, then A raised to power n is equal to 8 dots A raised to power n minus 1, where your n is greater than 1. Your n is greater than 1. That is, when you are having such a thing, you are having, maybe your n is 2, that means you are having n minus 1, which is 1. That is, you are multiplying matrix A by matrix A. If you are having your n to be 2, to be 3, that means you are having A raised to power n minus A raised to power 3 minus 1, which is A squared. That means you are having A multiplied by A squared. So you first find the A squared, that is, you multiply matrix A by matrix A before you now multiply A multiplied by the square. So you find the products. If they are of the same order, take note of that. Then we look at matrix transpose. I've explained that when you are talking of transpose, you are talking of rearranging. You rearrange. If it's in column, you change it to row. That is transpose. This is the interchange of row and column of a matrix A. It is denoted by A raised to power T. When you see any matrix raised to power of T, either matrix A, matrix B, or matrix C, any matrix raised to power T, it means the transpose. What does that mean? They are telling you that you change the row to column. This means that if A is equal to A1, then A transpose is equal to A2. Look at this example now. You have A2 to be equal to 2, 1, 3, then 2, 1, 4. Then to find A transpose now, that means the elements you have in A now, A2, you have 2 rows and 3 columns. 2 rows and 3 columns. If you want to find the transpose, it will be what? It's going to give us 2 columns, that is 3 rows and 2 columns, because you are rearranging. The first row will come to the first column. The second row will come to the second column. So you are going to have 3 by 2 matrix. You are going to have 3 by 2 matrix because you are having the first row, the second row, and the third row with 2 columns. You are following. Notes: A plus B transpose is also the same thing as A transpose plus B transpose. If we have it as a product, A dot B transpose, it's also the same thing as B transpose multiplied by A transpose. Take note of that. A dot B transpose is equal to B dot A, B transpose dot A transpose. Take note of that arrangement. Then we have a transpose, then transpose again. You will have it as your A. That is, to take the transpose again, you rearrange twice, you will still go back to your A. You rearrange your A twice. If you rearrange, to take the transpose twice, you will go back to the normal matrix. If A is a square matrix and A transpose is equal to A, that is, you have a square matrix and your A transpose is also the same thing as A, does not change. You still have the same entry. In such a matrix, we call it a symmetric matrix. Take note. We call it a symmetric matrix. If the transpose of A is equals to A, we have it as a symmetric matrix. In the other way around, if the transpose of A is equals to minus A, that is, there is a slight change in the entry. Maybe you have 0, 2, minus 2 is 0. By the time you find the transpose, you see that where the minus is before has changed. The position has changed to another point, another entry. That is, there is the sign as you have a negative sign on a particular entry there. That means that such a matrix is a skew matrix. So take notes. Any real matrix can always be expressed as the sum of real symmetric matrix and real skew symmetric matrix. That is, you can find the sum of those matrices. So look at the example we have here. Look at the entries of a matrix here. We have 1, 0, 0, 1. When you take the transpose of this matrix, that is the first row, which is 1, 0, bring it to the column, you also have 1, 0. The second row, take it to the column, you have 0, 1. So the arrangement does not change the matrix. So that is why this particular example demonstrates a symmetric matrix. That is an example of symmetric matrix. Look at the second one. 1, 2, then 2, 1. When you rearrange, you still have it as the same entries. Look at the third one too. They are all symmetric. Look at the Roman figure 2. It's an example of a skew matrix. You have the 0, 2, then minus 2, 0. When you rearrange, you have the 0, minus 2, then the next one will be 2, 0. So you see that the one that are having negative, the negative number there, it has changed from row 2, column 1. It has changed to row 1, column 2. So that makes it to be a skew symmetric matrix. So we want to look at another types of matrix again. We look at what we call a principal diagonal. Yes, a principal diagonal. When you have a matrix, you look at what are the elements you have in that matrix. How does those elements? What can you see about those elements? Let's look at the example we have here. Given that A is equals to AI, they are is a square matrix. Then the diagonal, which consists all elements of Aij, for which I is equals to j. That is, where you have the elements of the matrix, you know you have your I to be the row and your j to be the column. If the numbers of the row is equal to the numbers of column, that is where you have 1, 1, A11, A22, A33, A44, A55, T, A, M, N. That is, on those diagonal, if you have it that way, then you have it as a diagonal matrix. It's known as a principal or main diagonal of A, and it has been listed out here. The principal diagonal here is A11, A22, dot dot dot, T, A, M, L. This one is an example of a principal diagonal. Then we look at the unity matrix. A square matrix A, which is equals to Aij, in which Aij is equals to 1. Aij is equals to 1 for I equals to j that is for I equals to j. When you have the entries, you have the row 1, column 1 to be 1, row 2, column 2 to be 1, row 3, column 3 to be 1, row 4, column 4 to be 1, and so on. And all other entries, they are 0. Top of the upper one and the lower one. The upper of that one and the lower of that one. If you have the entries as 0, we call such matrix as a unity matrix. That is, your Aij is equal to 0 when I not equals to j. That is, when the numbers of row are not equal to the numbers of column, the element at that point is equal to 0. But when you have it as the same, when the numbers of row is equal to the numbers of column, you have the entries as 1. That is what we call a unity matrix. This matrix plays the role of an identity matrix in the matrix multiplication. So this one is what we also call the identity matrix. So when you are given a matrix, how do you find the determinants? We want to look at the determinants, revisions of determinants. What do you mean by determinants? Determinants is the value associated with a square matrix A of order n. The value associated to that matrix of the same order, that is the determinant. It may be denoted as depth when evaluate its value is given as depth A. That is, you put the entries inside a curve. That is, you put just like a modulus. You put the entry inside there, then you find the determinants. And that determinant is the same thing as the summation from j equals to I to n of aij, that is small aij, then capital Aij. What's the meaning of this? Your capital Aij is the new determinant. Is the new determinant from the main one, from the main matrix we are given. Is the new determinants of the square matrix obtained by eliminating the height row and the high column. That is, when you want to find the determinants, you want to find the determinants of a matrix A. You have entries. Looking at the first entry, your A11, that is the row 1 and the column 1. If you want to look at the points, if you want to find the values on that point, you are going to pick that value, then multiply by the determinant of another new matrix inside that place. That is, you are going to cancel out the first row and the first column. If you are picking the first entry, which is A11, you cancel out the first row and the first column. Then you bring out the remaining entries you have, which is taking A11, you are left with A22, A23, A24, then the second row, A32, A33, A34, then the third row, you have A42, A43, A44. That is the first one. Then come to column 2. On column 2, you have your A12. Bring it out, then cancel out that column and that first row. So when you cancel out, you are left with column 1, column 3, and column 4. Bring them together. Find the determinant again. The third entry, that is row 1, column 3. Cancel out that row 1, column 3. The other entries in that big matrix, bring them out and find their determinants. That's what we have here. Then, you are still having 3 by 3 in that determinant. That means you are going to repeat that procedure again. You are going to bring out, for the first one now, you are going to bring out A22. That is, you cancel out the first row and the first column. You find the determinant. You find the cross product of A33, A34, then A43, A44. You multiply them together with what you have outside, you will have your value. So if you follow that procedure, you will get determinants. What are the basic properties of these determinants? Let's look at them. The values of determinant remain unchanged in the event of interchange of row and column. That is, when you interchange the row and the column, you will still have the same thing. You still have the same value when you find the determinants. When you take the transpose of a particular matrix, you find the determinant, and when you take that matrix, you find the determinant, you will discover that their value will be the same thing. Then, an interchange of any two row or column change the signs of determinant. When you interchange, it will change the signs of that determinant. Multiplying all elements in any row or column by a scalar product of the same results as multiply the determinant by the scalar. That is, when you are given a matrix and you are also given a scalar, that is a constant value, you want to multiply them. When you find the determinant and you multiply by that scalar, your results will be the same as when you find the determinant and multiply by that the number, the constant value, which is your scalar. So the results are the same thing. So when you go through all these properties and look, for example, to establish what we are saying here, whether it's true or not. So we have, let V1, V2, V3, and so on to Vn be a row or column vectors of the square matrix A of an order n. The determinant of A is equal to 0. If and only if they are scalars, alpha 1, alpha 2 to alpha n, not all 0, such that the product of those vectors with the scalar is equal to 0, where your 0 is a 0 vector. That is, when you are given a matrix, you want to find whether they are linearly dependent or independent. You get the matrix, you multiply by the scalar, then you solve for that scalars. You equate them to 0. And mind you, the scalar, they are not 0. They are not 0. They are not 0. In such a situation, we call them linear dependent. If otherwise, they are said to be linear independent. Let's look at example to demonstrate that proof. The row vectors of order 3 matrix is given as this. We have your A to be equals to 2 minus 1, 3, 1, 2, 1, 1, 2, minus 1, minus 3, 4, minus 7. This is a matrix. The first thing for you to do is to find the determinant of that matrix. If you find the determinants of this matrix, you will discover that the determinant is equal to 0. I've given you the steps of how to find the determinants of the matrix by taking your 2, then cancel out the first rows and the first column. You are left with 2 minus 1, 4 minus 7. Multiply them together. You have 2 multiplied by minus 7, then plus 4. You have the value there. Add it with the second one. Perform the same operation. Then add it with the third one. You will have your determinants to be equal to 0. Then, to show now that they are linearly dependent, you introduce a scalar, and our scalar is alpha. You know you are having 3 vectors now. You are having 3 vectors. That is, we are having 3 rows. You're having 3 rows. Vector 1, vector 2, vector 3. So when you multiply them by the scalar 1, scalar 2, and scalar 3, you have a system of equations which is given here. 2 alpha 1 plus alpha 2 minus 3 alpha 3, which is equals to 0, that is equation 1. Then minus 2 and minus alpha 1 plus 2 alpha 2 plus 4 alpha 3, which is equals to 0, that is equation 2. Then minus alpha 1 minus alpha 2 minus 7 alpha 3 is equals to 0, that is the third equation. So when you use this is a simultaneous equation. So when you solve it, you can either solve by method of elimination, to find a way to eliminate one of the variables that you have here you reduce it to 2. Then from that 2, you get 1 out of the 2. You substitute your result into the next equation to get the next variable. Then when you get that, you also substitute to another equation to get the third variable. When you do that, you will have your alpha 1 to be 2, your alpha 2 to be 1, and your alpha 3 to be minus 1. You can see that you have equated all the 3 equations to 0, and with that, your value, your constants, your scalars, they are not 0. Hence, V1, V2, V3 are linearly dependent. They are linearly dependent. So we have established that. Then the next one, we look at what we call a singular matrix. When do you say a matrix is singular? A matrix is said to be singular if their determinants is equal to 0. And since when you are given a matrix and you find the determinants of that matrix, if it's equal to 0, that means it's a singular matrix. You cannot go further. You cannot solve. It's not that easy to solve. But when you are given a matrix and you find the determinants and you are getting a value, then you can proceed to solve that matrix. So in that case, it will be easy for you to find the inverse of that matrix. But if they are singular, you cannot find the inverse of that matrix. Let's look at the example we have here. A is equals to 1, 2, 1, 2 again. A is singular since the det A is equals to 0. So when you find the determinants of this, you have 1 times 2 minus 1 times 2 to give you 1 minus 2. I mean, to give you 2 minus 2, which is 0. That means this is a singular matrix. So if you tested a matrix and it's singular, you know that there's another way to solve that. You can't find the inversion, you can't find the inverse of that matrix. But if you are given a matrix and you tested, you find the determinant of that matrix, you are able to get a value, then you proceed to find the inverse of that matrix. And when you are talking of inverse, how do you go about that? Given a non-singular square matrix, for a matrix to have an inverse, it must not be singular. That is, it must be a non-singular matrix. Given a non-singular matrix, a square matrix A of order n, if there exists a matrix B such that AB is equals to I and is equals to BA, then B is called the inverse of A. That is, B is called the inverse of A. For you to find the inverse of any matrix, it must be a non-singular matrix. And when you multiply that inverse with the original matrix given to you, you will have an identity matrix, which we call I. I is an identity. You can still recall what an identity matrix is. When you have your diagonal as 1, 1, 1, the entry should be 1. while the upper one and the lower one will be 0. That is an identity matrix. Note, a non-singular square matrix A of order n has a unique inverse A raised to power minus 1 such that that is the inverse of A multiplied by A is equals to I. Is equals to I. And when you do that, you can find the inverse. The inverse is equals to the adjoint of a matrix, that is, find the transpose of that matrix over the determinants, where your Aij, the capital Aij, is the matrix of cofactors of Aij, and the Aij transpose, Aij raised to power t is the transpose of Aij. That is, you find the transpose. After getting your minor, you find the minors of that matrix. After getting the minors, you find the cofactor. You find the transpose. Then you introduce the sign. Then you have your adjoint divided by the det A. That will give you the inverse of the matrix. So let's look at the next example that we have here. Find the inverse of a matrix A. These are the entry for matrix A. We have 2, 1, minus 1, 1, minus 2, 3, minus 2, 1, and 2. So the first thing for you to do, find the determinants of this matrix. You know how to find the determinants. Take the first row and the first column. The first element in first row, the first element, the first entry, which is 2. So take it out, multiply by, cancel out the first row and the first column. What you have left, multiply them together with that 2, keep that value. Then the next one, do the second the second column. Cancel out the second column and the first row. Multiply the remaining entry, that is 1 minus 2, then 3, 2. Do that. When you do the additions and subtraction, your determinant is equals to minus 19. Your determinant is equals to minus 19. Then from there, find the minor of that matrix. How do you find the minor? I've explained. The minor is when you take the first entry, you cancel the first entry, that is the first column, the first row, and the first column. Find the determinant of the other elements you have in that matrix. Get that value, put it down. Do for the second one, that is the first row and the second column. Cancel out the first row and the second column. The remaining entries, multiply them together, multiply them together, that is, find the determinant. You will have your minus 4. Then, do to the next one, you have a minus 1. So, you cancel out the first row and the third column. So, the remaining entries, find the determinant, you will have your minus 5. So, if you continue that way, you will have a minor, which is given as your Aij. Aij. I haven't gotten that. Now, when you are doing that, you have to introduce the signs, which is a minus 1 raised to power I plus 1. That is, as you are multiplying, as you are finding determinants, you include that value. So, if you are first in the areas of sign, if you have your I to be 1, that means you are going to have 1 plus 1. That means minus 1 raised to power 1, minus 1 raised to power 2 will give you positive. So the first entries will be positive. The next one will be negative. The third one will be positive, the next one will be negative. So it will just be alternating the sign, till when you are through with, depending on the numbers of entries you have in that matrix. So having done that, you now find the transpose of that your results. You find the transpose. So that means I'm going to take the row to the column, follow that pattern, then you have that. That is your adjoint. We call that step an adjoint. So that adjoint divided by the determinant will give you the inverse of that matrix, which is given here. So the next one is a special matrix. What are the special matrices? We have the orthogonal matrix. Orthogonal. An orthogonal matrix is a real matrix A whose transpose is the same as its inverse. That is, we are given a matrix A. You find the transpose of that matrix, and you also find the inverse of that matrix. You see that their entries are the same thing. So that means that matrix is an orthogonal matrix. It's an orthogonal matrix. If A transpose is equals to A inverse, if they are the same, it is an orthogonal matrix. The term orthogonal is used in linear algebra to describe two vectors that are at right angle. So we look at another special matrix, which is a unitary matrices. A complex matrix whose transpose of its conjugates is the same as its inverse is called a unitary matrix. When you are talking of unitary, you are talking of a complex matrix. That is, the entries, the figures you have there, the elements you have in that matrix, they are a complex number. They are a complex number. So when you find the conjugates of that matrix, that is, whose transpose of its conjugates is the same as its inverse. So when you find the conjugate, that is, you revert the signs of that matrix, and the inverse of that matrix, if they are the same, we call them a unitary matrix. Example, given P to be a vector P11, P12, P13, and Q to be given as Q11, Q12, and Q13, then P transpose, that is the conjugate of P transpose, multiplied by Q is equals to, when you are talking of transpose, we are rearranging. We change the row to column, then you multiply by the next matrix, which is given as this. Then this scalar product, that is when you are multiplying the product, when you multiply these matrices together, this scalar product of P and Q are orthogonal if this scalar product is 0. That is, if you multiply them and the result is 0. If the vector are real, then the set of vector is called orthonormal sets. Take notes. It's called orthonormal set. That is, when you are given a matrix, a complex one, you multiply them, you find the conjugates of that P. Then you find the transpose of that P, you multiply by the next matrix, the products give you 0. If the products give you 0, then you have what you call orthonormal sets. If A is a unitary matrix, then A transpose multiplied by A is equals to 1. This implies that the unitary column vector is a unity vector. A unitary vector is a set of the vector x1, x2 to xn for which ai transpose multiplied by xj equals to, that is when they find the products, the transpose of that matrix and the original matrix. If the products give you 0, for I not equals to j, you have a 0. Then for I equals to j, you have 1. So we are trying to explain the orthonormal set and the orthogonal matrix. Let's look at the example that we have here. Let x1 be equals to a vector which is root 2 over 2 minus I root 2 over 2, then 0. And our x2 is also given as vector I square root 2 over 2, then minus root 2 over 2, then 0. And your vector x3 is given as 0, 0, 1. Then we want to do the multiplication now. We find the transpose of x1, that is x1 bar transpose. So you transpose x1. When you transpose x1, it's a column vector. You transpose it from that, it's just a single column. So when you change it, it will be in a row. Then you multiply it by that x1. When you do the multiplication, you will have your result as 1. Similarly, when you do for x2 and x3, you will have your result as 1. But in the other way around, when you put A1 and A2, when you find A1 transpose, you multiply it by 2. That is, when your I equals to j, the product will give you 1. But when your I is not equals to j, the product will give you 0. The product will give you 0. So we have it here to be equals to 0. Therefore, the set of vector is a unitary vector. It's a unitary set. It's a unitary set. So, if you have any questions, we will attend to that in our interactive class.